As you move into A2 maths, you may find that in questions that require you to differentiate, the equation that you are differentiating, whether that's to find its gradient or for some other function, is now a bit more complex. Either you're having multiple x terms that you can't combine together, or you have still a single x term, but it now has more operations connected to it. To help us solve these more complicated questions then, we have certain rules of differentiation that we can employ. There's the chain rule, the product rule, and the quotient rule. Now for the chain rule, first of all, this is where y is going to equal some constant times an x expression that's in brackets. I'm just using u here rather than x to represent an entire expression, like to represent x to the power 4 plus 1, like we have over here on the right. And then to a given power of b. To start off with differentiating that, you are going to begin the usual way. You are going to times your coefficient and your power together, and then you're going to take one away from that power. However, here, we're then going to multiply by the differential of what's in the bracket. What's in the bracket differentiated. And to be clear, I'm just using this dot here to mean that we're multiplying them together. We're getting a product. So in our example, if we have y equals 3, then brackets x to the power 4 plus 1, and close brackets to the power 5. The differential of this, 3 times 5 is going to be 15. Then the bracket as is going to have its power taken down to 4. Then this is going to have times to it, the differential of the bracket. When you differentiate, the 1's going to disappear. And here, x to the power 4 is going to become 4x cubed. And it's up to you at this point whether you would then times that all together. So you'd have 60x cubed and then brackets x to the power 4 plus 1, close bracket to the power 4. Or you just left it in that form. It may depend on what the question is asking of you, but that is how you will initially treat something if it's in brackets to a power. For the product rule, this is what you'll make use of if two different kinds of x terms are times together. Now, usually this will be when it's like completely incompatible operations, so maybe it's an irregular x term times by a trigonomic function, so a sine or a cos, or maybe an e to the x or something like that. For the purposes of my initial example, I will just be using like two regular x terms. Yes, you could times these together regularly and then just do a usual differentiation. In fact, we use that just to double check the answer at the end. And the only reason for this is because this idea of how we're going to differentiate e's and logs and all that, I'll explain afterwards. So for now, we'll just say that if you have u times v, where each of u and v are terms involving x, that the differential will be u dash v plus u v dash. And now when we say dash with these apostrophes, this is a notation you may find to represent saying that this letter has been differentiated. So whatever the u term was, differentiated, times by the regular of the v term, plus and then the other way around. Therefore, when we come to use the product rule, we first of all need to identify what our u and our v are. So u is going to be 9x squared and v is going to be 6x. Therefore u dash will be 18x and v dash will just be 6. To combine these together to get your dy over dx, so first of all u dash v, so the 18x times the 6x, that's going to get you 108 x squared. Then adding on here u times v dash, so 9x squared times 6, that's 54 x squared, and so together that makes 162 x squared. If we did just want to double check, as I suggested before, times these two brackets together, 9 times 6 is 54, and x squared times x is x cubed. Differentiating this, therefore, 54 times the power of 3 is the 162, and then, of course, the x cubed is going to drop to be an x squared. That is the same. This is how we can differentiate for things times together. Lastly, then, in terms of these three main rules, the quotient, instead of timesing this time, this is where your x terms are divided. In this event, start again with u dash v, but now we're minus uv dash, and that's also going to be over v squared. With this in mind, when we look to the equation y equals 5x over 3x to the power of 5 plus 8, we're going to begin once again by identifying our u and our v. So just on top here, this will be our u, this will be our v. Therefore, u dash is simply going to be 5, and v dash is going to be 15x to the power of 4. Combining these and plugging them into the equation, you therefore get dy over dx being u dash v, so this times this, that's going to be 15x to the 5 plus 40, then minus from that uv dash, so this times this, that's going to be 75x to the power of 5. This will all be over with 3x to the power of 5 plus 8 squared. You don't always need to expand this bracket on the bottom. You're usually fine just to leave it as is. This would technically be the simplified form. You don't need to expand if perhaps it then cancelled through in any way with something else. But again, usually you can just leave it as this. All we may want to do though, just on the top, is simplify here. So we're still going to have 40, but the 15x to the 5 minus the 75x to the 5 is then going to be minus 60x to the 5. And again, just this 3x to the 5 plus 8 all squared on the bottom. And just down here, we come to what I also mentioned earlier, which are just these other examples of what we can do with differentiating certain terms that there aren't among these rules, but can be used as part of these equations that require the rules. If you were to have y equals e to the u, and if you're not familiar with what e is, I would suggest going over the exponentials and logarithms topic. If we wished to differentiate this, this would be u dash e to the u. The e to the u term doesn't actually change. All you're doing is timesing in front by what the differential of this power is. And here I'll also just mention the integration as well, because it's virtually the same. I might as well. Now once again, the e to the u term stays exactly the same, but now you would divide by the integral, the differentiation of the power. So in this case, if we had y equals e to the power of 9x, the differential would be 9e to the 9x, because 9x differentiated to just 9, and therefore the integral would simply be 1 over 9 e to the 9x. Related to that is then the natural logarithm. You cannot integrate the natural logarithm, so we're just going to look at the differentiation here, which is fine because that's the topic of the video. ln u will differentiate to u dash over u. Now usually you'll see that the natural log of x, ln x, differentiates to 1 over x. It's not always the case that it is 1 over whatever's in the bracket. It's just because x differentiates to 1. If it had been, well, let's just see here, ln 7x minus 9, the differential of that, 7x minus 9 differentiated, is going to be 7. So it'd be 7 over 7x minus 9. Up here, this third one doesn't come up that often, but I want to mention it just in case, and that's where x is now the power rather than the main number. In the event of this, so y equals a to the x, the differential is actually y ln a, and I'll explain just the proof of that in a second, but to give the example, as if y equals 3 to the power of x, the differential therefore would be y ln 3. So for that rationale, if we took the original, okay, and we did a natural log of both sides, so yeah, the ln of y equals the ln of a to the power of x. Once you've done this, you could actually get rid of the natural log straight away on the left-hand side, making it y, by raising the right-hand side as e to the power. Again, if you're not familiar with why and how we can do this, I'd go back over the exponentials and logarithms. Also, just to save space, we'll say in this step, because you have a power inside the logarithm, you can simplify and bring that on the outside as a coefficient of the logarithm. Now the reason why we did this, because apparently we just went from y straight back to y, is because we may not know how to differentiate a to the power of x. But we do, from what was just on the left, know how to differentiate e. So when we now do our dy over dx, we can say that the differential of this power with respect to x is just going to be the ln a, and then you still have your e to the power of x ln a, and you know that e to the x ln a is the same as y. So this gradient here is the same as ln a times y, which will be the same as y ln a. Okay. Lastly, you then just have your trigonomic differentiation, so differentiating between sine and so forth. If you had sine of a to the x, this would differentiate to cos a to the x. So sine differentiates to cos, and if you then times by whatever the differential of what's in the brackets would be, kind of like we did with the chain rule. So in this case, you had a to the x differentiated would just be a. This, if you were to continue, would become negative a squared sine a to the x, because cos differentiates to minus sine, and once again you would be timesing the coefficient by the differential of the brackets themselves staying the same. So minus, then a times a is a squared, and then sine ax. Just to finish it off, that would then become minus a cubed cos ax, because minus sine differentiates to minus cos, and once again you would be timesing by the differential of what's in the brackets. In general, just trying to show here that sine differentiates to cos, differentiates to minus sine, differentiates to minus cos, and that would loop back around to the regular sine again. And if you have something more complex than a simple x inside of your brackets, you would want to times in front of the coefficient by the differential of what's in those brackets. So here, if you just had sine of 2x, that would become 2 cos 2x, which would go on to differentiate to be minus 4 sine 2x, which if you were to continue would become minus 8 cos 2x. These then are all the different concepts that we might want to employ when faced with a more complex differentiation question. Now, as you may have noticed, the structure of this video is slightly different. I've spent this first screen just going through all the various ideas. And following on from this, usually I'd give you a question of your own to try, and then would finish off by looking at a question lifted from a paper. But this time over the screen, I'm just going to have a selection of shorter questions, each of which will use any of the above rules. Let's see how we get along with them. So, just down here, we have these 6. Ideally, I would like for you to pause the video and have a go at this for yourself. If needs be, rewind to the previous screen so you can see all of the different tips and tricks for each of the various rules. Either way, we'll just go through one by one, pause if you want, and if you have, press play again when you're ready to compare. So, for the first question, we have y equals x plus sine 2x, all cubed. This requires the chain rule because it's something in brackets to a power. So, going by the chain rule of coefficient times power, 1 times 3 is just going to be 3. Then the bracket, as it usually would be, so x plus sine 2x, drop the power by 1, and then this will be timesed by the differential of this bracket. X differentiated to just 1, and the sine 2x, as above, is going to become 2 cos 2x. You have no obligation to actually times these out together, like span the brackets or whatever. You can just leave this like this. For the second one, we now have differentiate cos of 2x cubed over 3x. Because this is a fraction, we now have the quotient rule. So we should start off by identifying our u and our v. The u is going to be the cos of 2x cubed, and the v is going to be the 3x. u dash, therefore, is going to be, so the differential of this bracket will be 6x squared, and then cos becomes minus sine of 2x cubed. Beneath that, v dash, that's just going to become 3. So, plugging these into the quotient rule, starting off by u dash times v, so the 3 times the minus 6 is going to be minus 18, x times x squared is x cubed, and sine of 2x cubed. And this has minus from it, u v dash, so that's just going to be 3 cos 2x cubed. This then is just over v squared, so that'll be 9x squared. This you could simplify slightly if you wanted. You can divide through by a factor of 3, so the 18 will become 6. The 3 is now just a 1, it's just no coefficient at all, and the 9 on the bottom becomes that 3. Okay. If you so desired, you could split that up into 2 further fractions. You could say so minus 6x cubed sine 2x cubed divided by 3x squared. Well, the 6 will cancel with the 3 to leave you with 2. The x cubed will cancel with the x squared, just leave with the single x, so minus 2x of the sine. And then on the right, you would still be left with a fraction, so minus, and then the cos over 3x squared. If you so wished, just like the first one, you don't have to do anything beyond that. Thirdly, so differentiate x cubed ln 5x plus 2. These are multiplied, so this will be the product rule. So once again, we'll just identify our u and our v. So the u is going to be the x cubed, and the v is going to be the ln 5x plus 2. So u dash will be 3x squared, and v dash is going to be 5 over 5x plus 2. Timesing these together then in the formula for the product rule, so u dash v, so 3x squared times the ln, or simply 3x squared, natural log of 5x plus 2, there's no other real way to combine that, not simply, and then you add onto that the uv dash, so that then becomes 5x cubed on the top and still 5x plus 2 on the bottom. No way to simplify that further, that is your answer. Fourth, given that y equals 1 plus e to the 2x to the power of 3 over 2, find the value of the differential at this specific x value. So this would be from a slightly bigger question, where you're maybe looking at the gradients of curves. You could go on to talk about tangents and normals and so forth. If you want to brush up on what those words mean, those kind of questions, you can find the video on those topics under straight lines. In general, these rules may appear more as part of larger questions. Here, just focusing on how to apply the specific rule. If you came across a bigger question that required it, I would suggest also just finding the topic that larger question relates to and just combine the two concepts together. Here though, in general, once again, this is going to be the chain rule because it's something in brackets to a power. So a coefficient of 1 times the 3 over 2, that's just going to be, so 3 over 2, the bracket as it originally was, and then take 1 away from the power, so 3 over 2 minus 1 is just going to be 1 over 2, and you times this by the differential of the inside. The 1 disappears, and then the differential of 2x is 2, so that's then 2e to the 2x. If you wanted to simplify that in any way, I suppose you could do that because you've got divide by 2 and times by 2. They'd cancel with each other. So you'd have 3e to the 2x, and then 1 plus e to the 2x to the power of a half, but there's no obligation to. The main thing is now we're going to be plugging in this value for the x. So you'll have 3e. Now here, 2 times a half is going to cancel. And then so you just have ln 3. And that's going to be times 1 plus e. And once again, the 2 is going to cancel with the half, so it just leaves you with ln 3, and this is then to the power of half. E to an ln power, they cancel with each other just to leave you with what was inside the brackets. So here you would have 3 times by 3. And then here in the brackets, again, so e to the ln 3 is just the same as 3. 1 plus 3 is 4. To the power of a half is the same as square rooting. So the square root of 4, we'll just say is 2. Therefore, it will be 3 times 3 is 9, times 2 is 18. I suppose in theory you could also say that it would be minus 18 because you could have a plus and a minus square root. However, you obviously can't have two gradients at the exact same point. Therefore, we'll just go with that positive. Down back on the left, we now have given that y equals 3 sine theta over 2 sine theta plus 2 cos theta, and it's just given you a range that theta is going to be between so that this works. Show that you can differentiate to give something over 1 plus sine 2 theta. Well, this is the quotient rule, so once again we'll start by identifying our u and our v. So u will be the 3 sine theta, and the v is going to be the 2 sine theta plus 2 cos theta. U dash, therefore, is going to be 3 cos theta, and v dash is going to be 2 cos theta minus 2 sine theta. Putting these together into the quotient rule formula, so you're going to have your u dash times v, so that's going to be 6 sine theta cos theta plus 6 cos squared theta. That'll be minus uv dash, so 6 sine theta cos theta. And then a minus of a minus is going to become a plus. So then plus, so 3 sine theta times 2 sine theta, so 6 sine squared theta. All of this then gets divided by your v squared. So think of this as a double bracket. So 2 sine theta times 2 sine theta will give you 4 sine squared theta. 2 sine theta times 2 cos theta is going to be 4 sine theta cos theta. 2 cos theta times 2 sine theta will again be 4 sine theta cos theta. So together that's 8 sine theta cos theta. And then lastly, 2 cos theta times 2 cos theta will be 4 cos squared theta. Simplifying this fraction, 6 sine theta cos theta minus 6 sine theta cos theta is going to cancel, and 6 cos squared plus 6 sine squared. Well, from our trigonomic identities, sine squared add cos squared equals 1. So the fact that these are both 6 times each of those, that just means it's going to be 6 times 1, so it'll be 6. As for the denominator, similarly, so you've got sine squared add cos squared, but 4 sine squared plus 4 cos squared, so that would just be like 4 times 1, so 4. And then here, this middle term, there's another identity which, if we're not familiar, is sine 2 theta equals 2 sine theta cos theta. Is the double angle formula. We'll need it both for this question and in fact the next one, just for ahead of time. Employing this identity here, if 2 sine theta cos theta was the same as sine 2 theta, then 8 sine theta cos theta, that's 4 times as much of this. Therefore, that's going to be plus 4 sine 2 theta. We're now closer to what we were before. We just need to get this to be 1s on the bottom though. So if you want that to be 1 plus sine 2 theta, you need to divide through by 4. 6 divided by 4 will be 1.5. That therefore is your rational constant, A. Finally then, we just come to, given that x equals sine squared 2y, where y is between these values, find dy over dx, giving your answer in this form. where P cosec Qy, where P and Q are constants to be found. We'll deal with what cosec is in a little bit if you're not familiar already. I want to start though by pointing out that obviously here this is different to all the others because x starts as the subject and y is inside the function. The trick here is that rather than trying to do any kind of inverse, because that's going to get complicated, we can still differentiate as is. It's just that this will now be dx over dy. Now we can turn this into dy over dx later, but we'll start here and treat it as we usually would. So if we were differentiating this, this is kind of like the chain rule. Again, I'll just rewrite it. So it's like sine 2y, and then put the squared here. That makes it a little more obvious. The differential, so sorry, that should for now still be just your x. The differential of that, the dx over dy, is going to be therefore power times the coefficient. So 1 times 2 is just 2. Bracket as it usually would be, but then drop the power by 1, so it just becomes 1. But then you times to this the differential of what's in here. Well, 2y differentiated is going to be 2 with respect to y, and then sine becomes cos, so 2 cos 2y. If you were to just simplify this slightly, if you so chose, so your dx over dy, 2 times 2 will be the 4, so 4 sine 2y cos 2y, and then once again, based on this identity, we can say that if it was 2 sine and cos, that would become sine 2 theta. So 4 as a coefficient is double this. So we'll start off with a 2 sine. But then here, for what's inside, the coefficient of what's within the function is double the coefficient of what's in the sine and the cos individually. So theta and theta become 2 theta. Here, therefore, 2y and 2y is going to become 4y inside of the function. So right now, dx over dy is 2 sine 4y. Lastly then, to turn this into dy over dx, this is just that fraction upside down. So in other words, it's 1 over. So your dy over dx as we desire will be 1 over 2 sine 4y, which we can say is like a half times 1 over sine 4y, but 1 over sine can also be called cosec. So that's where we get our cosec for y. Therefore, we can just finish off by saying that P equals a half and Q equals 4.